Hello class. Today we're going to learn about Unit 7, which is about equilibrium. Everyone please turn on your laptops. Please turn on your laptops. Okay. So Unit 7 is about the solubility equilibrium and the common ion effect. So what is equilibrium? Equilibrium is a state in a reversible chemical reaction where the rates of the forward and reverse reactions are equal. This leads to constant concentrations of reactants and products. Now, it might look like nothing is happening on the surface, but the forward and reverse reaction rates are still happening, just at the same rate, and that's why you can't see a visible change. A saturated solution is a solution that contains the maximum amount of solute that can dissolve in a solvent at a given temperature and pressure. Additional solute added to a saturated solution will remain undissolved and form a precipitate. A precipitate is an insoluble solid that forms when two solutions are mixed or when concentrations of specific ions in a solution exceed the solubility limit of their compound. Here we have a demonstration. The sand is the solute and the water is the solvent. As we put the solute into the solvent, you can see at first this solution isn't saturated. The sand is kind of dissolving into the water, but now the sand is collecting and it forms a precipitate, meaning that our solution has saturated at this point.
Solubility product constant. KSP describes the extent that the compound dissociates into its ions in a solution. KSP is written as the product of the concentrations of the dissociated ions. Q is the reaction quotient. Q describes the initial state of the system in order to predict how the system will shift to reach equilibrium. If Q is less than K, then no precipitate forms. If Q is equal to K, the solution is saturated. If Q is greater than K, a precipitate forms. As you can see from the image on the bottom, AgCl is water insoluble, meaning that Q is greater than K, so a precipitate forms and it's insoluble. Dissociation is a process in which an ionic compound separates into its constituent ions in a solution.
Here's another demonstration where the sand is the Na plus ion, the gravel is the Cl minus ion, and the TNT is the energy needed to break the ionic bonds. So it's going to explode, and as we can see, individual ions have separated from each other, meaning they've dissociated.
Throughout. Factors that affect KSP. Temperature is the only factor that will significantly affect the KSP value. As the temperature increases or decreases, the KSP value may change. If the process of dissolution is endothermic, increasing the temperature will increase the solubility of the compound. Likewise, if the process of dissolution is exothermic, then increasing the temperature will actually decrease the solubility of the compound. As we know, adding heat will shift the equilibrium to favor the dissolution of the solid according to Le Chatelier's principle. On the bottom, we can see an example of the KSP product constant formula.
So what is the Le Chatelier's principle and solubility equilibrium? Le Chatelier's principle states that a system at equilibrium will adjust to counteract changes to its conditions in order to reestablish equilibrium. So on the right, we can see how a change in pressure results in a counteracting change. And solubility equilibrium is when a salt's dissolution and precipitation occurs at the same rate as a saturated solution.
Here's another demonstration. The snowballs in my hand represent me adding. So right now I've added reactants, and we can see that our equation will shift right. If I add onto both sides, this stays at equilibrium. But now that I have added only products, we can see that according to Le Chatelier's, we shift left.
The common ion effect is an application of the Le Chatelier's principle to solubility equilibrium. When a common ion is added to a solution, the solubility of the salt decreases because the equilibrium shifts to reduce ion dissociation. For example, adding NaCl to a solution containing AgCl reduces AgCl's solubility due to the common ion Cl-.
Here's our last demonstration in which we're trying to dissociate the nether wart. So this is our original solution, but this is the common ion solution, and I'll represent that by using glowstone dust. And now both of them are going to try to dissociate. And after a while, we see that in the original solution, we have fully dissociated. But in the common ion solution, it seems we have a bit more trouble with dissociating fully because of the common ion.
Question A says, a student draws a particular diagram shown to represent the ions present in an aqueous solution of strontium hydroxide. Identify the error in the student's drawing. One error is in the ratio of strontium ion and hydroxide ion in the diagram. In the diagram, the student has a 1-to-1 ratio when it should really be a 1-to-2 ratio. So for every 1 strontium ion, there should be 2 hydroxide ions. And because of this, the charges are also not balanced. So those are the 2 errors.
Part BI, calculate the value of OH minus in the solution. We know there's a relationship between SR2 plus and OH minus. As we can see from the equation, every 2 moles of OH minus are produced for every 1 mole of SR2 plus. Therefore, we know that OH minus equals 2 times SR2 plus, and OH minus equals 0.086 molar. For part B2, calculate the KSP. We know that the KSP value equals SR2 plus multiplied by OH minus squared. Plugging both the SR2 plus and OH minus concentrations into a calculator will yield 3.2 times 10 to the negative 4.
So for 3, it would actually be less than, because this strontium nitrate solution already contains a common ion, SR2 plus. So that means that the solubility of strontium hydroxide, which also has the SR2 plus ion, will be decreased, which results in a lower value of OH minus.